Dear students, after studying this module, you shall be able to learn about the basics about the self-assembly and self-organization processes, know how to distinguish between molecular self-assembly and supramolecular self-assembly, analyze self-assembly of inorganic architectures, and also understand self-assembly of organic architectures. Now let us begin with the introduction to self-assembly and self-organization. What is self-assembly, students? It is a spontaneous and reversible association of molecules or ions to form discrete or extended entities at either the molecular, covalent or the supramolecular non-covalent level. Within self-assembly processes, we must distinguish molecular self-assembly and supramolecular self-assembly. Molecular self-assembly concerns the formation of covalent bonds as a part of a special synthetic procedure. The assembly is subject to control by the reaction stereochemistry and the conformational features of the intermediates. For example, the formation of amine aldehyde condensation macrocycles. As shown in the figure, the formation of supramolecular self-assemblies results from the recognition-directed spontaneous association of a well-defined and limited number of molecular components under the intermolecular control of the non-covalent interactions such as coordination interactions, hydrogen bonds, and dipolar interactions that hold them together. The reversibility of supramolecular self-assembly is the key to resulting systems' ability to sift through the available components to form the thermodynamically most favorable structure. To put it in other words, supramolecular self-assembly concerns the spontaneous association of either a few or many components resulting in the generation of either discrete oligomolecular supramolecules or of extended polymolecular assemblies such as molecular layers, films, membranes, etc. The name tecton has been proposed for designating the components that actually undergo self-assembly. For your information, students, tecton actually means builder, and this spelling is T-E-K-T-O-N. However, the English spelling is T-E-C-T-O-N and it means builder. So, this is used for the components that undergo the self-assembly. Now, see this reaction here which we were earlier talking about. It's a shift-based condensation and the reduction of the product to give an amine. And second one, which is the B, is a macrocycle synthesized by aldol condensation of acetone and nickel En whole thrice 2 plus complex. Now, after having studied the self-assembly, we shall now concentrate on self-organization. It is a process which could be considered as a self-intersecting self-assembly, ordered self-assembly that would contain the systems presenting a spontaneous emergence of order in either space or time or both. Also, it would cover spatial, that is structural, and temporal dynamic features or order of both equilibrium structures and of non-equilibrium dissipative structures, incorporating non-linear chemical processes, energy flow, and the arrow of time. Thirdly, it would concern only the non-covalent supramolecular level. Next it will be multi-component and result in the formation of polymolecular assemblies presenting supramolecular organization and long range order with or without regularity and periodicity by virtue of specific interactions operating either through recognition events between the molecular components or in a dynamic process. The higher the degree of confinement or order, that is 1D, 2D, 3D, 4D, etc., of the self-assembled entities, the more they be considered as organized, that is molecular layers, membranes, micelles, colloids, liquid crystals, molecular crystals, entities, etc. Self-organization thus involves interaction, that is between parts, and integration of the interactions, leading to a collective behavior such as found in the phase change or in the generation of spatial or temporal waves. The phenomenological description of macroscopic features of self-organizing systems must eventually find an etiological explanation at the microscopic, molecular and supramolecular levels. Now, I would like to point out one more thing. Self-assembly and self-organization students of a particular supramolecular architecture are both multi-step processes implying information and instructed components of one or several types, and these may be distinguished from mere templating. Now, the question arises, what is templating? Templating is a synthetically most efficient procedure involving the use of temporary or permanent helper species of organic or inorganic origin or nature for the stepwise assembly of molecular or supramolecular structures of high complexity. Self-assembly and self-organization require molecular components containing two or more interaction sites and thus capable of establishing multiple connections. Self-complementary components associate with themselves undergoing homo-assembly, whereas complementary components, that is pleromers, associate with one another giving hetero-assembly. Now students, having studied the self-assembly and self-organization and also the templating, let us now come on to the study of self-assembly of inorganic architectures. Inorganic self-assembly and self-organization involves the spontaneous generation of well-defined metallo-supramolecular architectures from organic ligands and metal ions. So you can say they are organometallic in nature. The latter serves both as cement holding the ligands together and as center orienting them in a given direction. In the process, full use is being made of the structural and coordination features of both type of components, which in addition convey redox, photochemical or chemical functionality depending upon their nature. The formation of any complex species from an organic ligand and a metal ion is in principle an assembly process which occurs spontaneously. The emphasis here lies in the design of ligands and the choice of metal ions, so that in order to produce defined architectures in a controlled fashion from multiple subunits. Metal ions have properties of special interest as components of supramolecular systems and also linkers for the purpose of self-assembly. They provide a lot of advantages, like they provide one is set of coordination geometries available for coordinating with the organic ligands. Second, they provide a range of binding strengths varying from weak to very strong, and of formation and dissociation kinetics from labile to inert. Thirdly, they provide a variety of photochemical, electrochemical and reaction properties which are very useful in conducting many other reactions of industrial and other uses. In addition, and most significantly, they allow the reversible assembly, disassembly of supramolecular architectures and represent switchable interaction sites, for instance, by electrochemical interconversion between oxidation states of different coordination geometries. Let us take a specific example of self-assembly of inorganic architectures. Example is a self-assembly of double helicates, which is shown in the figure that you can see here. In the presence of copper 1 ions and a organic ligand, here the organic ligand is shown in figure. You can see here it is 2,2-bipyridine, also abbreviated as BIPY groups. A spontaneous assembly takes place giving double-stranded helicates in which two ligand strands are wrapped around each other in a double helical fashion, just like you can understand in the case of DNA, with copper 1 ions holding them together. It results from the tetrahedral-like coordination imposed by each of copper bipyridyl 2+ complex site from the design of the ligands, which disfavors binding to only a single strand. In such instances, a double helix formation requires self-recognition by two helicands, and that leads to preferential formation of the double helical structures. Now, I hope this example and this figure will clearly justify the self-assembly in case of inorganic architectures. Let us put it in other words. Helicate formation amounts to a tetrahedral reading of the molecular information stored in the bipyridyl strands. So, you can understand through this figure how organic ligand containing the 2,2-bipyridine or the BIPY group like B and C, they are showing you, are the double helical self-assembly of the copper 1 ions. Only metal ions presenting the appropriate coordination features with bipyridyl ion or the bipyridine complex will form double helicates. This is also shown to be the case for silver 1, which yields the tri, tetra and pentahelicates as confirmed by determination of the crystal structure of the silver trihelicate. Now, this can be seen here in the next figure. Using oligobipyridine ligands, the formation of triple helicates becomes possible through a modification of the steric instruction by shifting the 6,6- disubstitution to a 5,5- disubstitution, which should remove the hindrance towards the binding of 3 bipyridine units to an octahedral metal center. The above discussion has been clearly shown in this figure, students, where you can see that a schematic representation of a trinuclear double helicate silver self-assembly of Ag3 Bp3 whole twice and Cf3 SO3 whole thrice is shown, and in this B part you can see the structural view by an Orte plot, and the spheres represent 20% probability. In the C feature of this figure you can see the Muldrow plot with radii criteria giving a space filling model. I hope this concept is clear from this figure. A trinuclear triple helical complex is also shown in figure, is indeed formed by spontaneously by self-assembly from 3,5,5- disubstituted tris bipyridine strands and 3 nickel 2+ ions. Now, it is clearly shown in this figure how this complex is formed. Now, students, next I would like to get on to another topic is the nature and coordination of geometry of the metal ions involved in the self-assembly of helicates, in addition to 3 main features can bear structural information determining the nature and shape of the helical species formed may be distinguished. These are the precise structure of the binding site. It specifies in particular the ability to coordinate metal ions with a given geometry as well as the number of strands bound. Secondly, the spacers separating the binding sites. It must favor inter over intra-strand binding, and it influences the tightness of the helix, that is also known as the pitch of the helix, through the rotation of one metal center with respect to the next. Thirdly, most importantly also, the configuration of the coordination centers determines whether the structure is indeed of helical nature or not. Helicity basically implies that all the metal centers have the same screw sense, either right-handed or left-handed. The self-assembly of the helicates and related structures involves just one type of ligand and metal ion. Further progress in the understanding and the control of self-assembly and self-organization of inorganic suprastructures requires the conception of systems capable of spontaneously generating well-defined architectures from a larger set of components comprising at least two types of ligands or metal ions. The design and choice of these components must fulfill criteria at all three levels of molecular programming and information input that determine the output of the desired final species, that is, recognition, orientation and termination. Multi-ligand, multi-metal self-assembly has been achieved also by means of a flat ligand containing 3 chelating subunits. For example, the hexaphenyl hexaaza triphenylene shown in the figure and bipyridine derived ligands. The ditopic bis-bipyridine component shown in the figure is employed and 2 units and 3 bind 6 copper 1 plus ions to form cylindrical complex. This amounts to the self-assembly of 5 ligands of 2 different types and 6 metal ions. Altogether 11 particles to give you a closed cage-like entity all in one stroke in a spontaneous process. Now you can see here the A, B and C components, how A and B in different proportions they form the C component, which is a supramolecular self-assembled structure. Various other inorganic suprastructures are also shown as self-assembly, such as rack-like arrangement schematically represented would be formed by the complexation of several metal ions to rigid linear sequences of binding sites. A ladder suprastructure shown may result from the complexation of linear ligands and bis-pyrimidine derivatives or extended units with tetrahedral metal centers. Now you can see here that in this figure the A and B components are inorganic bis-pyrimidine ligands and the C component is the resulting ladder-like self-assembly constructed from these organic ligands. Now I would like to take up and discuss the self-assembly of organic supramolecular structures. The self-assembly of organic supramolecular species makes use of interactions other than metal ion coordination, such as electrostatic, hydrogen bonding, van der Waals forces, stacking or donor-acceptor effects as found in proteins, nucleic acids, liquid crystals and molecular complexes. The spontaneous generation of organized structures depends on the design of molecular components which are capable of self-assembling into supramolecular entities presenting the desired architectural and functional features. The nature of the species obtained will be determined by the information stored in the individual components. Thus, the self-assembly process may be directed by molecular recognition between 2 or more complementary subunits so as to form a given supramolecular architecture. If these molecular units incorporate specific optical, electrical, magnetic, binding etc. properties, their ordering may induce a range of novel features in the resulting supramolecular structure. Depending on the subunits involved, the association may lead to either supramolecules or to organized assemblies such as membranes, molecular layers, films, mesophases, polymeric species or even solid state lattices. The self-assembly of supramolecular structures via molecular recognition between complementary hydrogen bonding components has developed into well-defined arrangements of molecules in solution. in liquid crystals and in the solid state as well. The buildup of two-dimensional and three-dimensional architectures requires the presence in the molecular components of two or more hydrogen bonding subunits whose disposition determines the final supramolecular architecture of that organic moiety. When two subunits are incorporated into a single group, it will then possess two recognition faces and may be determined or may be termed as genus molecule. That is, meaning a double-phased hydrogen bonding recognition unit. If the faces are the same or different, the unit is homotopic or heterotopic. If the unit is self-complementary and may be termed, then it may be termed as plerotopic. Now considering the tridentate sites of 2,6-diaminopyridine and uracil are complementary single site groups as shown to you in the figure, while the next figure is plerotopic by virtue of its two complementary sites. On the other hand, if you notice, barbituric acid and 2,4,6-triaminopyrimidine or triazine are genus molecules containing two identical recognition sites, and these may associate either as linear or as cyclic structures. Each recognition site may be monodentate, bidentate or tridentate depending on whether it contains 1, 2 or 3 hydrogen bond donor centers or acceptor centers. Of course, the stability and selectivity of the associations depends upon the nature and position of the centers. The bases of nucleic acids are very well known heterocyclic groups that interact through hydrogen bonding, usually forming base pairs through Watson-Crick type association, in which flavin adenine dinucleotide, that is FAD, contains complementary adenine group and uracil site of the flavin. Now this is shown to you here. As I was earlier talking about this figure, it shows here the complementary single site groups of 2,6-diaminopyridine and uracil and B, which is the plerotropic group. Next figure shows you the self-assembly of either a supramolecular ribbon, that is right at the top, or the supramolecular macrocycle, which is at the bottom, from barbituric acid and 2,4,6-triaminopyrimidine units. The self-assembly of a porphyrin or its zinc 2 complex, that is the zinc 2 plus ion complex bearing two uracil groups by means of two TAP units, yields a supramolecular bisporphyrin cage as shown to you, into which a bipyrimidine guest molecule may bind by coordination to the zinc 2 plus sites in a synergic fashion. Now this is showing to you the figure is showing to you the self-assembly of a supramolecular bisporphyrin cage with the zinc 2 plus ion. Now students, after having studied what is self-assembly, what is self-organization and what is self-assembly in both organic and inorganic architectures or structures, we shall now summarize this module. In this module, you have learnt that self-assembly is a spontaneous and reversible association of molecules or ions. Also, these building molecules are known as tectons, literally meaning the builder, to form larger, more complex supramolecular entities according to the intrinsic information contained in the molecules themselves. We taught you that fundamentally self-assembly is a convergent process in which a number of components they assemble into ideally a single final stable structure. Self-assembly is thus very distinct from chemical emergence, which is only a divergent process in which complexity evolves over time. Self-assembly broadly is divided into two classes, that is self-assembly, as I told you, of the inorganic structures, or the self-assembly which is the second part of the organic structures. So these are the two classes into which the self-assembly is divided. Next, we came on to the fact that inorganic self-assembly and self-organization involves the spontaneous generation of well-defined metallo-supramolecular architectures from organic ligands and metal ions. Next, we came on to the self-assembly of organic supramolecular species, and this makes use of interactions other than metal ion coordination such as electrostatic hydrogen bonding, van der Waals forces, stacking or donor acceptor effects as found in protein, nucleic acids and liquid crystals as well as molecular complexes. Now students, supramolecular chemistry is taking our world by large amount of interest. So I hope this particular module on self-assembly and self-organization has made a lot of interest in your minds.